Okay guys, welcome back. Makeba bafowethu. Kusewuye. Hope nisase kahle. Hope you're still good. Please guys, subscribe to the channel, like, share the channel. Share it to everyone man. Ubatshela ukuthi beze la ekhaya kaMakeba siphathana kahle kakhulu. Siphathana kahle kakhulu. Ubatshele nje siyakhula. Thank you so much futhi guys, ngiyabonga kakhulu. Isandla dlula ikhanda. I see the channel, it's growing very fast. So uMageba nje uthi isandla dlula ikhanda. Okay, siqhubekeni bafowethu ngomsebenzi wethu. Namhlanje we'll be doing classification of some stationary points, where we do the local minima and the local maxima, where we just the local minimum and the local maximum. Then how do we find those things? We're still looking in terms of the graphs, and also if we don't have a graph, if now f prime derivative of a is equal to 0. F prime of a is equal to 0. I hope you still know what is this. We called it, when we f prime of a is equal to 0, this is what? Stationary point. This is the stationary point. And then and where f prime second derivative prime of a is greater than 0. Your f prime of a equal to 0, then the f prime second derivative of a is greater than 0, meaning inkulu kuno 0, meaning this number here must be positive. Then your f has a local minimum. At x is equal to a. So just draw the function here. Is your point A. This is our local here, our local minimum. I hope you see it. I hope you understand it. I hope everything is pashash. I hope yonke into iyabonakala. If f prime of a is equal to 0 and f prime of a second prime, meaning second derivative of a, is greater nkulu kuno 0, then this is a local minimum. See, we call it a minimum because here we have our graph, it's where it's at our lowest point. It's where our graph is at our lowest. That's why it's a minimum. And then if f prime of a is equal to 0 also, and now f prime second function of a, now it's less than 0. I hope you see the difference. This is the same, but the difference is here in terms of the f prime, the second function, the second, not second function, sorry guys, sorry, the second derivative, then when it's like this, then f has what? The local maximum at x is equal to a. Have a local maximum. This is the local maximum at point A. I hope you see that one. I hope also you do understand the logic. Very important. This is very important. This is very important. This is very, very, very important. If it's greater than 0, we have a local minimum. If it's less than, meaning it's negative, than 0, meaning it's a local maximum. And also there's something we call a stationary point of inflection. What is that? What is a stationary point of inflection? Let me just do a graph for you. At this point, I hope you've seen this thing. This graph is one of our classification where we interpreted graph, where our graph is increasing, and then here comes to this point, which is we call it the stationary point, and it also increases again, where here decrease comes here, and then also when it reaches this point, it also decreasing. This we call this a stationary point of inflection. Why? Because this a stationary point of inflection, it's either neither a local minimum or a local maximum. It's just a stationary point, so we call it a stationary point of inflection. There is no maximum here, there is no minimum here. In this point, there is no maximum here, there is no minimum here, so this is just a stationary point of inflection. La, it's where f prime of a is equal to 0. Also f prime of a is equal to 0. There's no this thing of greater and less than, it's not here in this one. I hope you see the difference. I hope you see the difference. We're just gonna go to the example now of explaining these things. Now from this example that we have here, they are saying the point of 1 mapped to -1 and the point of 3 mapped to 3 are SP layer. This one stands for stationary point of the function f is equal to -x cubed plus 6x squared minus 9x plus 3. Then they are saying classify each of these stationary point as local minimum or local maximum or stationary point of inflection. Stationary point of inflection. There is a point here, point of inflection. Not gonna use this one. And then how do we go about that? Doing our solutions, we need to find the first derivative of our function. How do you find it? We derive it by -3x squared plus 12x minus 9. After deriving it, we need to find the second derivative, because our second derivative, that's where we get the clarification of everything that we need. Deriving this is going to be -6x and then plus 12. From this now, from this, now we need to substitute our x value in our second derivative, because in our second derivative, that's where we have to see that our second derivative at a specific angle, it's greater than 0 or less than 0. Then we can see that is our local maximum or local minimum, or it's just the stationary point of inflection. So substituting in our second derivative, gonna substitute 1 because 1 is just one of our x values in the coordinate, so just -6 into 1, then plus 12. We're getting what? We're getting 6. 6 is just 6 is greater than 0, which is just f prime of 1, it's greater than 0. What does this mean? If our f prime, second prime of that x, specific x, which is 1 in this case, it's greater than 0, meaning this is local minimum. I hope you understand that one. I hope you do understand that one. And then now when x is 3, second derivative where x is 3, -6, x is 3 plus 12, we get what? -6. Now -6, it's less than 0, ncane kuno 0, -6, meaning f prime of 3, it's less than 0. What does this mean? It's telling us that f is, or f is this f is what? A local maximum. If, guys, make sure you understand this thing, if your f second function, or not second function, second derivative of that specific x value, it's greater than 0, it's a local minimum. X second derivative of that specific x value, it's less than 0, less than meaning it's negative than 0, meaning f of that function has a local maximum. I hope you do see the difference between the two. We are doing local maximum, local minimum, second derivative. That's where we determine the local minimum and the local maximum. Thank you so much, guys. Thank you very much.